Yeah, but I'd have to record
recording
it.
ourselves lately. Are you putting it on YouTube?
No. I figure someone in my family, grandma or grandpa, will want to watch it. They can't follow.
I didn't know if it's for the.
Self-reflection.
Okay. I was just curious if they were coming public.
No, but we should. Someone should record Mark's again.
That seems like it's on you.
Yeah, I would, but this is my last marks.
Last marks ever.
My first mark.
You also my first marks.
Huge.
Mark.
Oh, great news, I printed.
You proved it?
Yeah,
Oh, that's
you may
easy.
just need to show up the side. Yeah. I don't know why I didn't think about just finding locations and breaking the cases. I think I was stubborn. I was like, I don't want to do cases.
You proved the whole thing, or?
It's not, so
Just
far,
the
that
entries?
they're all the same. I even show they're non-zero. I suspect that, like,
I know. This
yeah, I
is
think your
surprising.
mention probably works as like a negative sign, so.
Sorry.
You missed the curling last night.
I was exhausted.
You were too busy being tired.
Kyle, if you wanna speak next week for a special marks Thursday to say goodbye. No one's gonna be here.
I'll come.
No pressure.
I'll go.
Just if you were sad about it. I'm good. Okay.
You expecting anybody else?
I don't know. I don't think so.
Okay. Well then, let's get the party started. Ross doing his part B on tropical site classes and heterogeneous. Right.
Cool. So I want to start by basically motivating tropical geometry for about the 100th time in Marx. What is tropical? And there's a good chance that this stays on the board forever because I forget about it. So you've heard one answer a bunch before, and this is that it's some kind of combinatorial shadow of algebraic geometry. It's a line we kind of say to keep ourselves alive. But this is not necessarily how I think about it. I want to intrinsically motivate the study of tropical geometry as its own geometric, like a geometric theory in its own right. So we want to introduce basically a category of tropical objects to study. Our starting space is polyhedron. So a polyhedron, we're going to just think about as some kind of finite intersection of half spaces living in some Rn. This lets us get things like line segments. I know I drew an arrow on there. Line segments, your classical like polyhedra that you think about. Squares, we can intersect basically the four planes defined by the edges of the square. Yeah.
Are yours always bounded, or
They can
just
have
like-
edges out at infinity in some sense. You really are taking these in like some t to the n, and so you identify with some r to the n with some infinite boundary. Okay, and then a polyhedral set necessarily, we're just gonna take unions of these things. And these are going to be our local model for the geometry we want to study, right? So in the same sense as when you try to approach like smooth manifolds and you have some local model of some Rn, our topological sets are going to admit some local model of polyhedra. And what do I mean? Okay, so our first definition, a TPL space, is some topological space X. And what it's going to come with is that every point X in X has some neighborhood U of X and some homeomorphism. And some homeomorphism from U to some open set of some polyhedral set. And it's got to be like paracompact in Hausdorff, but we're not gonna worry about that, yes.
Sorry, what does TPL stand for again?
Tropical piecewise linear.
Oh, okay.
The piecewise linear space part will make sense in a moment. So some examples, everyone's favorite that they've seen, the tropical line before. If you've come to Renzo, me, or Aaron's talks. For example, it's like kind of vertex here admits some neighborhood that's homeomorphic to this polyhedral set, the union of 3 of our line segments. And any one of the edges just admits the same kind of thing. And you can get some things that you wouldn't consider necessarily like tropical in the sense you've maybe seen it before, because you can get objects that do have kind of curves. But still, every neighborhood or every point admits a neighborhood that has this kind of structure. Okay, now the piecewise linear part. We don't just want to do topology, we want to do geometry. If we want to do geometry, there better be a sheet floating around somewhere. And so what we're going to do is we're going to give X a sheaf we're going to call the piecewise linear functions on X. So now a TPL space is really some topological space along with the sheaf of piecewise linear functions on X, such that whatever this local chart is, on open sets it induces an isomorphism of the pullback sheaf. So I should say, locally it's doing this. Piecewise linear functions on V, and piecewise linear functions or V are really given by linear functions on whatever the kind of generating set for your polyhedrons. They're honest piecewise linear functions. Okay. So this was the kind of thing that your original paper with Chan and Ulrich and Weiss studied when you were looking at cone stacks, but we want to enrich this category a little bit. So right now we're looking at just TPL spaces. And so we want to move on. So this is what I can call a TPL space. We want to move on and define what we actually think of as a tropical space. One thing I forgot to mention, any one of these topological spaces also admits the constant sheaf of functions, just R, just constant functions. And so a tropical space is going to be some TPL space equipped with an affine structure. And for now, that's going to be pretty general. So we have some topological space X equipped with an affine structure. And the only thing I'm going to require of this affine structure right now is that it lives between constant functions and piecewise linear functions. And so we have a wide range of things available to us, right? We can take all TPL spaces are now actual tropical spaces. We can take them with their constant sheaf, still consider them tropical spaces. So you can kind of be as arbitrarily close to the TPL structure as you want, and as arbitrarily close to the constant structure as you want. Okay, and we do this kind of to enrich this, because this is gonna have, it's just has too many functions in it. It's not gonna really pick up kind of the intrinsic geometry that's happening. It's gonna have too little, where you're not gonna pull any information out. So we want some good choice for affine affects. Okay, so the first thing we're going to consider is going to be harmonic functions. And so the sheaf of harmonic functions, I'm going to define it by giving germs, really, or even you could do small open neighborhoods, but we're thinking of this as functions that when you look in the tangent directions and you sum along the slopes, you actually get 0. So, an example of this, let's look at our tropical elliptic curve, because it has genus 1. In the neighborhood of this point, we kind of have, so actually let me call this point P. In the neighborhood of this point, you have functions, function whose slope along each of these in total sum to 0. So you can have some slope A, some slope B, some slope C, where I'm thinking of these as linear functions in each of those directions, such that A, B plus C equals 0. And so the germ here is really,
The red segment's supposed to go in the same direction as the black segment?
Yeah.
Okay.
sorry, not great representation there. Y plus C, Z, and I'm just thinking of these as coordinates on each of these. Plus some constant shift such that this condition holds, A plus B plus C, 0. Whereas for just our piecewise linear functions, so if I were to take this as a TPL space with just the piecewise linear function, at P, I don't have such a condition. Less, Z. So this is really like a C3 plus some constant shift. And for constant functions, you just have constant functions. There's technically a line. Okay. So these three different sheaves give out three different germs over this same point. So even though this curve it stays topologically the same when we consider it with these three different sets of structures, they're three completely different tropical curves. Okay.
Sorry, and what you're meaning is that you could choose either one of these three sheaves to be your alpha,
Yes.
and that would make it.
Yeah. So this half was just some arbitrary choice of a sheaf falling in between here. These are three sheaves that have different germs around this point, and so you get three different tropical spaces.
That says Z3 plus R.
Yeah, so when we're looking
Plus
at the,
what?
huh? When we're looking at the piecewise linear, there's no condition on the balancing of these slopes, so we can kind of choose them completely independently.
But that's not reading the translation factor is a real number or constant.
Yeah.
But A and B and C have to be integer.
Yes. Yeah, part of, sorry, I didn't include this fact, but now that you're saying it, I guess it's important enough to at least say is that when I look at the piecewise linear functions on a polyhedral set in specific, so over a polyhedral set, if we're thinking about this living inside of some Rn, I have to be the restriction of some function that looks like this. Rn is living in.
Gotcha.
Yeah, sorry. So we end up having choices of only integer slopes.
Wait, I also have a question.
Yeah.
So you can have different slopes on the either sides of the loop?
So for this one, I'm just looking at germs. If I were to try and create a global section for this guy, well, not even a global section. If I just, oof. The answer is for germs, yes. You can't really make a global section of this because you won't get a continuous function if you pick some slope m along here and you try to follow it. As it winds around, you'll end up coming in at the right slope, but you don't get a continuous function. But when you look at germs, you can't actually pick these kind of things. Okay. So we know what a tropical curve is. Well, no, a tropical curve is now one of these with dimension 1. I've introduced tropical space. We have some conditions. So, at this point, my goal is to study psi classes on genus 1 tropical moduli spaces. I'm going to want to study how curves vary in families, right? And the notion of stability for curves. So I want to introduce 3 things: smoothness, stability, and what I mean like family-wise stability. So, small piece of information I've left out is that this curve actually comes with some genus function as well. And this is going to be a function, gamma x to z, that just assigns a genus to points. This is because we're going to end up allowing points of higher genus when we get certain degenerations. And so a smooth curve is going to have, if gamma of p is greater than 0, then whatever choice I make for f, this should just be constant functions. Then whatever choice I make for f should be my harmonic functions. Well, the drill is there. And if p is infinite, then I should only have constants. So what this is saying is that if I have some higher genus point, whatever my sheaf is that I've picked for f should look like just my constant functions. I shouldn't being allowed to have slope going into some higher genus point. P is finite. So you asked earlier, Mark, if we're allowing these things to have faces sitting at infinity, that's basically what's going to determine whether this point is infinite or finite. And it's the idea that if I have some function with some actual slope going off to infinity, it's going to go to infinity, and we're not going to have good behavior. So P is finite. You can think of it actually sitting within some finite volume. And there I want to be looking at harmonic functions if I want a nicely behaved curve. Okay. And so if I want a stable curve, so a stable curve, then every genus 0 vertex gets at least 3 half edges. And that shows up in something like this, where every vertex gets 3 half edges, even if one of them ends up being a bounded edge. And genus 1 has at least 1 half edge. So if you're the kind of person that just sees me drawing a bunch of dual graphs, you'll see how this recovers the kind of stability conditions from classic algebraic geometry.
Does genus 0 have at least 3 half edges, or exactly?
At least 3 half edges. Yeah, you can have one. Yeah, this is one. Okay. So, I've defined a bunch of objects that I'm calling tropical objects. What are we missing?
Avenues.
Not quite.
Oh.
We have the objects of the category, but we don't have the maps between them. We can't make a family unless you know what a morphism is. There's some life lesson in there that I'm not gonna unpack. Okay. So, morphisms. We want our morphisms to be honest morphisms of the underlying topological space. So, x to y, if I'm taking two tropical curves or spaces, x to y should be a continuous morphism of the underlying topological spaces. It should map, I want to make sure I get this right, should map push forward PLY onto push forward PLX in such a way that maps the affine structure on Y into the push forward of the affine sheaf on X. So that you're going to come from some sort of morphism of TPL spaces with just the piecewise linear structure, and you're going to respect whatever affine structure you've then attached to these topological spaces. Okay. Now we can get families, because we understand what a morphism should be. So, the start of a family is a pair of tropical spaces, F and B, and a morphism between them. So for example, I'll just do one side for now. So for example, we can have this family over what is the tropical line, and actually we'll consider it impacted by, so this has its infinite face. So this is T1, whose fibers are stable tropical curves. T. And so what's actually happening here is really the starting point is not a family between tropical curves. Sorry, I actually want to say this, we should first have a family of TPL curves. So TPL family will be some map pi that respects the affine structure or it respects the piecewise linear structure of both these maps, and the curve. Then we can get an affine family of tropical curves. If we have an affine structure, if we can give F and B an affine structure that pi still respects. So there will always be some kind of underlying family of TPL curves, but then give F, comma B, that pi still respects, and such that the affine function structure restricted to the fiber makes FB stable tropical curve.
No.
Okay. Okay, but then we have another notion of, we have one more thing we have to add before we call it an actual stable family. And so assume I've gotten my favorite family of tropical curves. And so, at least in the topological picture, I drew this and then realized I didn't talk about it. At least in the topological picture, this family here has as fibers tropical elliptic curves. So I'm thinking of this as that kind of cone on the bottom, so that each fiber living above it is actually a curve that looks like this. And then one more condition for stability, so stability in families. Is that if I have some affine function living on my top space, so I have family, f over b. If I have phi living in the affine structure of f, such that phi restricts to fiber. The restriction to some the fibers is constant. Around B, there's an open set and some phi. Sorry, let me write it down and then not talk anymore. Okay. If I have a function that restricts constantly along all the fibers of this family, then I want there to be some function in the base space around some neighborhood of the point over that fiber, such that when I can pull back some function from the base space to get phi. So the things moving kind of traversely across here, the functions with some kind of non-zero slope, traversely but zero in this direction, should be the pullback of functions from the base space.
This is a requirement that you're making for
For
FE
stability.
to be a family, or to be
Not
stable?
for family, but for stability, yeah.
Be a stable family, okay.
So is there any notion of that's parallel to flatness?
Not that I
I
can.
mean, a flat family in regular algebraic geometry really enables you to prove lots of theorems. So I was wondering if there's some analog here which would be useful in that same parallel way. Okay.
Yeah, nothing I've thought of so far, but
I mean, one thing that you can do, you can, for example, fix the discrete invariants that, the genus and, tropical curves.
This is a consequence of flatness. Flatness tends to be a little technical, of course.
Yeah. So I mean, I'm not aware of like a similar technical definition made in this piecewise linear setting that would yield those as consequences. Most commonly, people just go straight for like, well, fix the G in the end. Those are the factors we consider.
thank you for the question, though. Interesting food for thought. Okay, I'm not going to go terribly deeply into this, but the original work on thinking about these kinds of things, or at least doing it over moduli spaces, was a lot of Renzo's collaborator Hannah Markwig, thinking about these in genus 0. And so, without too much more detail, there is an affine structure on M0 n plus 1. Oh, and all of my moduli spaces are tropical, if I ever do this. That makes it a stable family over M0n in a way, in a non-trivial way that lets you do intersection theory on just M0n itself. And so if we can do it in genus 0 with some kind of non-trivial affine structure, why can't we do it in genus 1? Okay, we've done a lot of setup to get to one of my favorite families. Oh, I actually want to introduce one more thing. Apologies, I out-ordered myself. So our goal is to study psi classes. I should tell you in passing what a psi class is. So the most generic definition for a psi class on a space is going to be that's my awful attempt at a Gothic L. It's going to be the first Chern class on the ith psi class will be the first Chern class of the ith cotangent line Boolean space. The definition we're going to work with for families of curves is that in families of curves, I can define my pullback, my cotangent line bundle by taking pullbacks of sections of the family map. So F is going to be some map from family to B. No, that's a lie. I'm going to have some map pi, some map F to some moduli space. And if F is the family induced by whatever my map into the moduli space is, and S is a section of pi, so S a section of pi. Negative. I haven't told you what that sheaf is yet, but
So MGN bar has a universal family, right?
yes, but it's only a universal family for TPL curves. Not, this is a problem, yeah, that I'm gonna try to avoid talking too much about because it's very technical. The universal family over MGN is only a fine moduli space for TPL, families of TPL curves, not generic tropical curves.
So what does it
But so-
mean to say that that's a moduli space then?
It's really some kind of moduli stack. Like,
Okay, Oscar.
yeah, we can talk about that later because it will take us.
Stack
It's a stack.
It's a stack
Okay.
associated with
It's-
families of tropical curves with affine structures. And ends up not being a geometric stack, so it doesn't have a finite atlas that you can use to kind of
Oh, okay.
think of the universal
I see.
family. I mean, you could have like an infinitely presented universal family if you want.
So it's not a tropical
Space.
space. Okay.
A tropical stack.
Thank you.
Okay. So, what it is, at least as a TPL curve though, it is a fine moduli space. And so, we can get a family like this arising from the map to this as TPL curves. And this is the family that I'm going to want to talk about for the rest of our time. So at least you can get this map, this family arising as TPL curves, and then we're just going to give it some extra affine structure and ignore what's going on over here. Even though this, as a moduli space for genus 1 TBL curves, is a fine moduli space, every fiber is basically only controlled by its length of the loop. Okay, so I want to actually compute at least the degree of a psi class on our left family. Kind of put that in the middle of the board, even though I want it to stick around. Okay, because I want to explain first what this f of minus si is. F of minus si is going to be the subsheaf of whatever affine sheaf I'm about to tell you is on there, with poles prescribed to a certain order along the image of this section. What is this section? So now we're just going to get a big one. And we're thinking that this has been compactified, so we actually have our edges at infinity. If we had embedded this into TP2 in some way, which I'm going to talk about in a second. So I'm thinking of this top edge lives at infinity, these side edges live at positive and negative infinity respectively, and I have my map pi, and pi here is just given by the projection downwards. So the section I want to take is the infinity section of pi. So we're going to think of S as having an image up at the having the image up at the infinity along the top line. The affine structure I want on this family, which I'm going to call the dreaded Smiley family, is going to be generated. So affine things will be generated by fiberwise harmonic functions. And pullbacks to an atlas that I haven't written yet. Okay, so I'm thinking of this family as really being glued together by four plane orthons. I think that's the right word. Where the bottom two here, L minus and L plus, correspond to the two cones here. So L minus here, L plus moving over here. And that's the last you're going to hear about those two for this story. Because I've chosen this section at infinity, we're not going to think too much about what's happening down the cones. The ones that are important for us are these two, which I'll call T minus and T plus, and give some coordinates. Y minus and X minus. So let's take a look at the affine structure we get if we're thinking about pullbacks being affine and fiberwise harmonic functions. So it's not the last you'll hear about it, because we'll look at this real quick. Yeah, 10 minutes. We're living. So Smiley of this neighborhood. So it looks like this kind of tripedal rose. behind. And it really should be an open neighborhood. So imagine dashed lines. Our choice of slope along this direction is completely independent of our choice along each of the petals, but the choices along the petals actually have to balance, and so we get something like, it's really because this looks like line across this tripod. And so we should expect up to constant shifts, things that look like a choice along here and then a choice of the harmonic function along here. So something like ax plus by plus cz, choosing these three to be the coordinates on here, and some md plus some r, such that we're at least balanced in the group order, ABC. If we choose some,
Sorry, can I interrupt you for a second to make a point that you think is important? So I kind of disagree with that equality that you put there. I would put a question mark over equality, right? Because
yeah, we
so
haven't fully given.
from your definition of stable family of tropical curves, you have that those fiber-wise harmonic functions and those pullbacks should be in the affine structure of those spaces.
Yes.
And then you say, are we so lucky that if we look at, at these functions, we get an affine structure in the total space?
Yeah, and that tells better into the story of where I'm gonna try to pull back around the central fiber. And thank you. Okay.
Now you're showing that in certain areas, yes, we are so lucky.
Yeah. So on certain parts, that's fine. We can, like, this is just gonna work out. So I'm thinking of this having the coordinates I've given from this top chart, and this is really here, where I can kind of just choose a pair of coordinates, ax and by, and it's fine. Okay, and now the story of where we don't get so lucky. Because of how we originally defined these pullback functions on the TPL spaces, we don't really have a good notion of what it means to pull back along here, because these aren't open sets down here. If we ever include any points along that central line. And so our remedy, at least the one that they originally cooked up, is to introduce some transition data between these top two charts. And this really corresponds to choosing some way to embed the top two planes of this into some TP. It really should be some TP1 squared.
I would call it more like a necessity than a remedy.
Yeah,
If you want an affine structure, you need to give that data. It does not come just from those
not magic.
conditions. Right?
Yeah. So we need to introduce some transition data for our coordinate functions on our charts. This corresponds to somehow embedding this top cone into a TP1 squared. And we can give it by y plus is y minus, x minus, and x plus is negative x minus. So this kind of y direction gets embedded with some slope along the lines, with respect to the perspective of the y plus chart. Okay, we kind of have all of our components to actually try and calculate what a pullback should be. Because now I can take actual, I can actually think of some function, ax plus by, and write out what it's, well, let's just do it. So now I can think of functions in here as ax plus by plus some r. And on this coordinate chart, I have the values of a x plus b y plus r, and then over here it takes values a, negative ax minus, plus b y minus minus mx minus plus r for whatever constant shape we have. Okay. So I want to compute whatever this pullback is of my cotangent line bundle by pulling back information along this section. So f of SI, if I consider this open cover of, this is image of S1, is this infinite bar up top, and we'll call this U and V. I can pick a section from U So what this is going to be is really things that look like minus y minus plus some r. So we can't.
But you haven't told them why. You
I
haven't
was
told
about
them
literally.
why.
Wait. Like why
Okay.
is
What
x
sheaf is f of minus si?
This is the subsheaf of f of happy with prescribed orders along the poles. Poles along the image of SI.
Did you say that I missed it, or
I think I did, yeah.
you did? Okay, sorry. Nothing.
So if I try to take some x minus here, it's not balanced along our, because we have infinity inside of this open set, so this can't be a regular section of this, well, a section of this, over this open set U. So we just get that our B slope is 0 in that direction. And the same story is going to happen for f of minus SI of V. So the negative slope in front of these is being imposed by the fact that I need to have a pole of exactly order 1 there. I don't know if I've explained what having a pole means, but we think of having a pole as a negative change in slope as we go along the fiber. And we think of, when we get to infinity, this flattens out, and so it has, I might have reversed signs. I think we want a +1 so that as we go to infinity and we flatten out, we get a negative change of slope, and it has a pole of order 1 there. Okay, we can't pull these sections back because they have poles along the infinite pole, or the, can't pull a section back with poles along the image of S, which at infinity. Because it has poles, or S has poles, and you would just get the infinite function, like the function that has value infinity everywhere. But what we can do is take the difference and pull back a cocycle for our line model. So, I'm trying to decide where to go, sorry. So on their intersection, on U intersect V, if I take their difference, and I'm gonna choose the same R so that it cancels, minus y plus minus x, skipping a step, plus R. What I do get is y minus plus R, minus y minus minus mx minus r. And so our y minuses kill, our r's kill, and we end up with just the function mx on this interior, which we can pull back because it doesn't have poles along the image of S. And what this looks like down here is really the cocycle MX on some open set inside here. Okay. And so the pullback of the line bundle we get on this family from that original map into the moduli space is something with degree M.
Sorry, what was M? I mean, I know it came from the gluing data, but did you say what it was?
Oh, no, I should have specified it's an integer, but we haven't chosen it yet.
It's a choice, though.
It's a choice,
Oh,
that's
okay.
the punchline.
Okay, sorry for.
You're
stealing
good.
the thunder.
So this is gluing data in, well, actually, we're at about 350, so I won't go into how this is gluing data for a line bundle. You can ask me about that later. So this is gluing data for whatever the pullback of our cotangent bundle is. But because we originally had kind of a 2-to-1 map into the moduli space, we want to make a choice for n, right? And that's kind of our whole game, is we want to make a choice, and turns out you can make the choice such that you recover the 1/24th of classical moduli space, the integral of psi1 over m11.
So what is it? What's the M that makes that?
It's 12. Because you have a 2-to-1 map.
So
Yeah, it's 12 or it's 112. 112. So it's, m didn't have to be an integer actually, m could have been anything. That's my bad, because I was working with the multiplication. Is 112. And the only motivation for that is really to recover that classical result, because that was a basically completely free choice. But, and this is just the end of the story, the idea is because the moduli stacks for tropical curves are in fact stacks, MGN in general. What we want to do is create a better behaved space that we call VGN, that I won't go into terrible detail about, that acts as an atlas for the moduli stack, so that we can actually compute these kind of intersection invariants over here, and with the correct notion of degree, push them forward onto the moduli space. And hopefully, what I'm working on is basically that this is the only choice you get in the entire sequence for genus 1. And what do I mean by that? I mean that you can create this for any number of mark points. This actually behaves reasonably well when you look at the universal family, and hopefully via combinatorial recursion of some form, kind of the same kind of stack dilaton relation, string dilaton relations that you get in regular moduli space theory, that choosing this in V11, which is not exactly the family I've shown, but is basically the family I've shown, is the only choice you need to make on this entire chain to set all of the invariants.
Any questions?
I have a sort of question, because I don't know if I missed or not. How is that cotangent line level defined? Because like you mentioned that there's no like universal family, so like what do
You just define it by its pullback to everything else.
So that definition right there is how you're defining it? Or, okay, so you're defining a bundle such that it pulls back in this way, or
Yes, it is the bundle that pulls back this way to anything else.
and this ends up being like unique by like just chance?
No, not chance.
Oh, there's like good
definitely some
reasons why
category
it ends up.
theoretic
Okay.
thing happening that gives it.
So, just a technical question. I remember the balancing condition you had for a three-valent vertex. And then I missed somewhere why you couldn't have X's on these charts here. You said it was also from some balancing condition?
For these two, yeah,
Yep.
at infinity. If I have any positive slope going there, I have some kind of, I don't have balancing. So I need to kind of be constant going out to infinity.
What's the vertex and what are the directions?
So it's gonna be some node at infinity. And so I really only have constant functions as germs along this node. There's no way I'm gonna get a section that restricts to agree with one of these if it has any positive slope in that direction.
Okay.
So is there a correspondence between psi classes and tropical psi classes?
You can read Renzo's paper with Andreas as of like, I don't know, a month ago, of when the psi classes that show up here are actually tropicalizations of like a classical psi class in some sense.
Too busy running your thesis.
Or watch his I think you do that IAS or something, yeah.
And what is C, so you said what LI is, but what is C1?
First term class.
Yeah, but where does it live in this context?
So, yeah, there's a weak Chow ring floating around that I didn't necessarily want to go into detail about, but we can talk about. And so this really gives us the degree of the pullback as a class rather than, yeah.
Operational child debates. You can feed it Minkowski weights and it will produce a Minkowski weight of one dimension lower.
Cool.
Is that this one okay?
Yeah,
Or any
nice.
question? No?
Love it.
All right, if nobody else wants to torture Ross anymore, let's keep going. Happy summer, everybody.
So what, I know we talked about this in the office, but what was the math?
Your computer, I think it made like a really high-pitched noise. I think so. I heard something.
That wasn't.
It was?
I don't think that was
Oh,
Ian's computer. I was hearing it from behind
Oh, okay.
Ian's head.
Gotcha.
No, it was like,
Like ghost.
you know how Weber,
Did I understand?
like you know how Weber will occasionally just make us
Double cover when you count,
noise.
So just set theoretically.
Oh, yeah,
are you just
set theoretically.
collapsing?
Set theoretically, you're 100%
And so I remember we had this question about isotropy groups. So did you figure that out?
No. But as far as I understand it, some combination of this being a SAC and the isotropy groups being like a too low dimension, or along this line here, when you consider this as the SAC M12, is what prevents this from being a geometric SAC.
But
From
I'm sorry, I
getting
just have a much
extra
simpler question.
Yeah.
Like what is the automorphism group of a general fiber and then of this special fiber?
So in the general fiber, you have like a mu2 thing living here.
And then what's the automorphism?
And at these points, it's this flip. So these will be curves. Points in here are gonna correspond to curves with some finite length.
No, I'm asking, take a point on the base.
Yeah.
Oh,
And then look
oh,
at the fiber.
Yeah,
that
the fiber is an elliptic curve, right? So it
Yeah.
has a mu2 that corresponds to flipping the loop.
So, and that triangle there is a loop, not a triangle, right? Or is it a triangle?
So it depends, so it's, if you think of it as M12 trop, right? Then you need to put sort of a B mu2 orbital structure along this diagonal and on this flap, so that when you fiber a product with a point, with a map from a point, you actually get an elliptic curve. That's the confusing thing.
that's the thing that still confuses me.
So like, I don't know why you have two sheets, but if you just looked at the first sheet here, the Z2 is like reflecting through the whiteboard, so it flattens these, and then you get mu2 on the bottom and mu2 on the x-axis.
So you get mu2.
So I'm saying
here.
there's a mu2 action that
Yeah.
just reflects.
Yeah.
And so here you have isotropy, and here you have isotropy, and here you have isotropy.
Yeah.
Okay.
Yeah. And so if you've seen the picture of M12 drop, right, with this triangle here, and you say, how is this map a universal family? Once you put this isotropic structure on this whole, into over here, and now you do the fiber product, you get a map from an honest point into here, right?
And this.
Basically, this doubles,
That's
right?
if you need to,
This is all we need
Yeah.
to do as well, right?
yeah.
So this should be a point mapping to half a point, right? And so you should get sort of a degree 2 cover of this
Yeah.
line here, but which is really honestly 2 only here and here, right? And everywhere else is 1, right? So you get actually this little mapping.
Yes.
But that's, you know, separate from the issue of like, I mean, this is a double covered space, right? But it's not an atlas of the space because it's not sort of subjective as a map of stacks. Because, well, you can put infinitely many different affine structures in this family.
I see,
So
because of that gluing.
because of that group, right? So if you choose one, you get one possible map, but there's a bunch of other possible maps that are not, sort of, that are independent from this one.
So there exists a correct choice of affine structure
So,
that
yeah.
makes it a universal.
Right, so Ross's project is saying, what if in the one case of M11 for this particular double cover, we make this choice of affine structure, which in fact is kind of like an orbifoldy choice, because we're in tech, if
Yeah,
this were a
it's
tropical
not an
space, you
entity.
wouldn't
Yeah.
be allowed to take 112 as a transition, but we're saying, okay, well, a finite isotropy is not what's gonna worry us at this point. So you make that orbifoldy choice, and then hopefully, for every other number of our points, you can induce a unique sort of affine structure on the corresponding atlas for M1N such that, you know, all the intersection theorems like classes match. But essentially, where the only choice that you have to make is this one. That's sort of like the initial. But this is, yeah, this was tremendously kind of annoying, the fact that like, you have infinitely many possible affine structures.
Yeah. I wanted to ask, I mean, my understanding from the first part of your talk is that looking at spaces which are locally polyhedral.
Mm-hmm.
Why is it locally polyhedral? What am I?
So there we
I
just.
see it at all these other places, it's
We
locally
need some kind of
polyhedral.
homeomorphism, right? So I guess the structure we're getting. It's not a lot. You have something like this and then 2 cones, right?
You have these 2 cones, which you can't escape from.
No, but you can flatten them out with it if you're just asking for topological homeomorphism.
But it comes
Why
that.
is-
Are you saying you replace it with like 3 triangles?
But yeah, so you're really saying the neighborhood of that vertex, right?
In the neighborhood at this point here, why is it locally
Well,
polyhedral?
because you're saying you can't really get rid of that.
Can you?
I mean,
Well,
does
that's a
it,
really good point. Sorry.
doesn't it depend on,
I'm having a brain fart right now.
so, like, it depends on what your I mean, you know, you could take 3 triangles and glue them together, and that topologically is the same as a cone.
Yeah.
Are you doing something like that?
I'm just imagining
So.
flattening the cone and then you still have.
Oh, yeah, I think, yeah, sorry.
some kind of-
I think that the cone,
you
yeah,
flatten the cone.
flattening, it's not like that you're flattening, but you can, essentially you can subdivide the cone into 2 parts, right? And each part maps to a triangle. Right, so it's not
I agree,
that
if
space.
you start
Yeah.
cutting this,
Yeah,
open,
yeah,
you
Yeah,
can
so
decompose
prob-
it,
so-
you can decompose it into locally polyhedral things.
Yeah,
but-
so probably that's what we want, I mean, like.
It's not a cone, it's 2 triangles.
So polyhedral space is
Oh.
something which is obtained by kind of gluing together.
Yeah, there was a fine point where you have to be locally homeomorphic to a polyhedral set that's a union of polyhedral things, right? So we can break that into kind of its other
Okay,
shape.
that's the finesse is this part.
Yeah, but, yeah, thanks, that was.
Yeah, yeah. I think I literally sat down and asked myself this. Or Aaron asked me when I gave this practice talk.
Alright, good. Good luck. Nice talk, thanks.
Alright, thanks, Rick.
So why did you have two sheets here?
I mean, my best answer is that this really arises from something called cycle rigidification.
No, I mean, you're so in love with
Yeah,
segregation.
I think that's right.
I think that the real reason to have two sheets here is that right here, you can balance, right? You have a vertex, right? So there's no way that you can put a reasonable notion of affine functions here other than just a constant.
Yeah.
If you want to balance
Okay.
at this point.
Okay.
So in order to have some
In
notion
order to
of
say what it means to be
to balance, you need to at least double cover.
Okay.
So you double cover, it's okay, now balance means what you think it means, X is balance, like slope one like this and slope one like
Yeah,
this.
okay.
And that allows you to say that,
That's
okay,
the
well,
issue, that's why there's not a unique way of.
but then, you know, you balance horizontally, but vertically, like you could
Choice.
have a
Oh,
shear.
okay, I
a choice
understand
of
now.
shear,
Okay,
right? So
thank
that's
you.
that's the issue.
This is a degree four.
This,
not
I
a
mean,
degree two.
I think that,
It's a degree two now.
what?
Sorry, I'll let you finish what you were saying first.
No, I think that, so I was telling Ross that, I mean, the reason you really like this VGN is that a way to sort of really kind of, in general, construct this analogous thing is by saying we're also like kind of doing a cycle verification of tropical curves, but that's just a way to describe it, right?
Okay.
The reason we want something like this is really we want to have some affine functions here, so that there's a meaningful notion of balancing. And the simplest thing to do is to double cover.
It's the same thing that went wrong up with F minus S at U at infinity, is like there's just no good affine functions at that point at infinity. And so it gets the slope. I mean, not this anymore, it would be two separate. Also, I think it is a double cover.
Oh, it's a degree four.
Blackboard.
Is the reflection quotient.
Oh, I mean, but this has a premium two, and this also has a premium two, right?
Well, if that's true, then this shouldn't be a cone, it should just be a triangle like that, right?
Oh, sorry. Sure.
Okay.
Yes.
Alright. Okay, I see what you're saying.
Absolutely. I don't,
Well, there's an intermediate, there's an intermediate which is just.
If you're putting, I mean, sorry, I was neglecting the premium
Ah.
two there.
yeah.
This covers that, and this
Yeah.
covers that.
Yeah.
That's two, that's two.
Okay.
And Renzo was talking about this one.
Yeah. Yeah, so I mean, yeah.
Sure.
In the end, we might need to be taking like a 1/6 instead of 1/12. That actually isn't bad, it's even closer to being integer.
I'm happy to improve your thesis.
Factor two.
Yeah.
Cool.
But I mean,
Interesting
so,
stuff.
yeah.
And so, okay. And then the question I had for Ross in office hours, or when he came to talk, was what's the isotropy at
Vertex point?
At the vertex.
at this point? And like, it has to at least be B mu two, and why?
That is an unsettled thing.
Okay.
I mean, I've witnessed, it's weird,
Right.
lots of kind of discussions between Jonathan and Martin and,
Yeah,
you know.
because that corresponds to like a generic elliptic
Yeah.
curve, right?
Yeah, but I mean, the thing is like, do you want to like arbitrarily put an isotropy based on algebraic data?
Mhm.
Or do you want to just put the isotropy that comes from the combinatorial data, in which case you actually don't have isotropy?
Yeah, but that's weird.
Which is weird, except that everything always reverses, right, when you go tropical.
Yeah,
so-
yeah, it's
so
weird
it's
though.
like- Yeah, it is weird to have like,
Yeah.
kind of like something that looks like, something that specializes to something with less isotropy.
There must be.
So, yeah, bottom line, I don't know.
Cool. It's a brave new world.
Yeah. Yeah. Cool.
Alright, thanks.
Nice talking.
Thank you.
I said pass.
So you pass it?
Yeah.
Cool.
All right, well, if you insist.
I'll leave the final decision to you.
If you insist.
Thank you, guys.
All right. What year are you, Ross?
Second.
Okay, so you finished your part A, right?
Is that quals?
I think so, yeah. Yeah. I got an email from Tenzia.
About?
Well, Donovan
Oh, yeah.
did his part B before his part A, and I had forgotten that that was not allowed. So. So it should apply.
I have colorful things in Italian in my mind.
That was it. Okay, no problem. Yep.
I mean, these are exactly the things that I wanted to like get rid of when we worked on these keys, like all this possible nonsense, you know, like you have to like first lift your left leg and then close your right eye, you know, that order, because if first you close your right eye, no, that's not, you know. That's
These are good.
Nice.
Different.
ways.
System, yes. A new dance.
Yeah, keeps us on our toes.
I had to, argue for, well, I did a master's before, with Montserrat, if you know her. And I had to argue for my master's courses to count towards the completion, because Tufts honors the graduate courses with a 2 in front of them.
Donovan also had that issue, which is why he's having this issue. But it's okay.
Oh, my actual qualifiers, they didn't know, right? I had to take 3 more, but.
Okay.
Cool. All right, well,
Anyway.
all right. Tell you lots a little bit.
Back to work. Got you. Thank you, guys.
We could just be in here until those go through. Yeah, perfect. Most of the words. Do you want to or no? Okay. Yeah, that's for the window.
Wanna do your history assignment?
Yeah, I'm going to do that first.
How many steps do you think it's over there?
I know how many. Like 11,000.
That would be really nice.
Yesterday I took 13.
13,000?
Well, I don't know.
Tuesday, 27. Monday, 17. What did I do on Monday?
13,000 steps.
so significant about that one specific?
It's connected to I didn't even.
They try to cover, they try to hide it.
How has it influenced global attitudes towards nuclear primacy?
They try to make more strict rules on it. I forgot what explosion, I think like someone was doing too much.
Somebody's on a scooter with a bin.
Oh shit.
What's your opinion?
Was that someone's water bottle that we got? Oh, this is
Okay. Sorry.
Oh, you
I
good.
thought it was.
Do you need me to call the phone?
Yeah, give it a try. I actually think I turned it off silent once. It's not in here. Thank you.